Hi everybody, and welcome to the third lecture in our final unit on galaxies and cosmology. The topic of this lecture will be the expansion of the universe. Like a lot of the topics that we covered in the celestial motions unit, the story of the birth of cosmology, which is what we'll be talking about today, is centered around a few key people and discoveries. Unlike celestial motions, however, many of the big questions of cosmology, such as what is the nature, shape, or fate of the universe, are unanswered. Cosmology is very much an evolving field of modern astronomy, with approximately half of all funding going towards investigating big unanswered questions like those I've listed here. In this lecture, we'll begin to talk about these questions, and we'll undoubtedly raise a few more to be answered in future lectures. To start, consider this image. This is a snapshot of a very famous image taken by the Hubble Space Telescope called the Hubble Ultra Deep Field. The story of how this image came to be taken and what it tells us about the universe is a great one, and so you'll explore this image in depth in lab next week. For our purposes here, though, all you need to know is that this is a long exposure image of a small patch of dark sky, and that every single speck you see in this image, which is with the exception of these two, which are foreground stars in the Milky Way, is a distant galaxy. Each tiny smudge is a galaxy with billions of stars. To start our story of the birth of cosmology, which, as I said before, is the branch of astronomy dealing with the large-scale structure, fate, and evolution of the universe, let's imagine that we take spectra of galaxies in this field. As we've discussed in previous lectures, in most cases we learn a lot more by taking a spectrum of an object than we do by taking a picture, as powerful as this one is. So say we look at this bright one here and disperse its light to create a spectrum. What will we see? Think about it for a moment before I tell you. What do you see if you take a spectrum of a galaxy? Well, we might see something like this. The spectrum of a galaxy is not so dissimilar to a stellar spectrum, except that you see the light of billions of stars combined instead of just one star. Galaxies, therefore, usually exhibit absorption lines, just like stars do. So let's compare this spectrum to what we might see if we looked at one of these smaller smudges, say this one. This is also a spiral galaxy, and so its spectrum looks very similar, but with one key difference. The absorption lines all have the same spacing and thickness, but are shifted toward the right, toward the red end of the spectrum. If we took a spectrum of this even smaller speck, we might see this trend continue, and the lines shift even further toward the red. In fact, with the exception of our nearest neighbor, Andromeda, which you learned at the end of the last lecture shows the opposite effect in its spectrum, the lines being shifted towards the blue, nearly every other galaxy in the night sky exhibits this effect. The absorption lines in their spectra are shifted toward the red end of the spectrum. As Maria discussed last time, this phenomenon of red and blue-shifted galaxy spectra was first discovered by an astronomer named Vesto Slipher, who worked at Lowell Observatory in Flagstaff, Arizona. At the time, astronomers had observed a wide variety of so-called spiral nebulae, but as Maria discussed, there was a great debate about whether these objects were local clumps of gas and dust in our own galaxy, true nebulae, or distant galaxies beyond our own. Vesto Slipher took spectra of a number of these galaxies and recognized the pattern of absorption lines, but noted that in most cases, the pattern was shifted redward relative to stars in our own galaxy. By 1924, he had accumulated 45 such spectra, of which 43 of them exhibited this redshifted effect. 45 doesn't sound like all that many, but recall that, as many of you discovered at the star party, galaxies are very faint, and that by dispersing their light, you make them even fainter. This was all before modern CCD cameras, too, so all of this work was done with photographic plates. 45 of these very faint objects was quite an accomplishment at the time. We call this phenomenon where spectral lines are shifted toward longer wavelengths, redder colors, redshift. Vesto Slipher had discovered that nearly all galaxies in the universe are redshifted. But what does this mean? To understand what it means, we have to review something that we talked about a bit in the context of planets a few lectures ago, but haven't covered in detail in lectures so far, which is the Doppler effect. The Doppler effect is defined as the change in the wavelength of a wave due to the relative motion between the source and the observer along the line of sight. The Doppler effect can manifest itself for any type of wave, including both light and sound. Although for astronomy purposes, we're concerned with the Doppler effect for light, since sound doesn't travel across interstellar distances, and if it did, it would do so quite slowly, here on Earth, we usually experience the Doppler effect as a sound phenomenon. You've probably heard the Doppler effect many times before, without ever really registering it as something special. One place where it's experienced most frequently is when something loud, like say a motorcycle, passes you. If you're ahead of the source of sound versus behind it, does it sound different? In other words, do person A and person B in this diagram hear the motorcycle as the same? Let's look at a simulator to investigate this question. Okay, so in this simulator, we are going to have a source and an observer. So this mark S is the source, and O is the observer. So I'm going to start emission from the source of the wave, and you can see what we're essentially depicting here with these circles is the crest of, say, sound waves that are emitted from this source. So when the source is stationary, they're coming out at regular intervals, making perfect circles, which they will always do. But something different might happen if I move the source toward or away from the observer. So before I do, what we're seeing in the panel here is the wave as emitted from the source. So essentially, like from the source's perspective, what does the wave that they're emitting look like? And then from the observer's perspective, what does the wave that they're receiving look like? That's in the second panel here. So I'm going to move the source away from the observer first, and we'll see what happens to these perfect, evenly spaced, symmetrical wave crests. I'm moving the source to the left here, and as you can see, when the wave is emitted from the source, notice that it's always circular, right? From the source's perspective, it's just emitting these perfectly circular waves. Here I'm going to move towards the observer since I ran out of room here. But as the source is moving towards the observer here, every time it emits a wave, it's emitting it from a little bit closer to the observer. So it's essentially catching up to waves that it's already emitted. So you can see that in the direction that it's moving, which is towards the observer here I'm going to go away. So in this case, in the direction that it's moving, which is away from the observer here, so if the observer were on the left-hand side, they'd be receiving waves that are more closely spaced. The source, by moving in this direction, is compressing the wavefront in the direction that it's moving. And here I'm going to move towards the observer again. We're compressing the waves in the direction of the observer. Now notice that in the direction away from the observer, and in this case I'm just going to move the source the other way. So in the direction opposite where the source is traveling, you have the opposite effect. The waves are being stretched out. So you can see these things manifesting themselves in what the observer is receiving. Notice that the top panel, the source panel, has not changed at all the entire time that I was doing this. You always have this perfectly symmetrical, evenly spaced waves. But if I'm moving the source towards the observer, once those waves catch up to the observer, so there's also an effect of light travel time here, they're going to be compressed, and now I'm going to pass the observer. Oh, I guess I can't, I'm going to move the opposite way. Here, tell you what, let's move the observer so that we can pass him. So I'm going to move the observer here so that I can move the source so that it's first approaching the observer and then moving away from the observer. So as I approach them, I'm compressing my wavefront. You'll see that it's starting to get shorter, the wavelength of the wave that's received by the observer. And then as I pass them, it's starting to get longer. The time between receiving wave crests is increasing. The wavelength is increasing. Okay. To summarize, the motion of the motorcycle, so you can see again what I was demonstrating here in this diagram, the motion of the motorcycle means that person A and person B in this diagram don't hear the same thing. Person B is in front of the motorcycle, so the sound waves emitted by the motorcycle are emitted from a bit closer to person B with each passing second. This has the effect of sort of compressing the sound wave, decreasing its wavelength. For person A, the motorcycle's motion has the opposite effect. Since the motorcycle is moving away from person A, sound waves are emitted from a bit farther away every second, effectively stretching out the wave and increasing its wavelength. So we've established that the motion of a source of sound relative to the listener changes the wavelength of waves, but how do we detect increasing and decreasing wavelength as human listeners? Let's listen to a few actual clips, and as you listen to them, see if you can A, identify the moment that the object emitting the sound passes the observer, and B, put words to how increasing and decreasing wavelength manifests itself in the sounds. So here's a car passing the recorder while blasting its horn. Here's a helicopter passing the recorder. Let's turn the volume up first. Here is a jet. And finally, and maybe most interestingly, an ambulance with its siren blasting approaching the recorder. Did you hear it? Can you tell what the effect of increasing and decreasing wavelength is on sound waves? And I'll give you a hint, it's not the volume, although we often hear things as louder when they're closer to us. There's another effect here. For sound waves, wavelength corresponds to pitch. The sound goes up a bit in pitch as the motorcycle or ambulance or helicopter or jet approaches, relative to how it would sound if that object were stationary. And it goes down in pitch when the source is moving away. You should have noticed an abrupt decrease in pitch at the moment that the vehicle emitting the sound passed the listener in all of those sound clips. This is the Doppler effect in action. The Doppler effect works the same way for light, decreasing or increasing wavelength according to whether the source of the light is moving toward or away from the observer. If it's moving towards the observer, the wavelength is compressed, decreased, and if it's moving away from the observer, the wavelength is stretched, increased. There are several real-world applications of the Doppler effect for both light and sound. Doppler radar tracking of clouds, sonar to detect objects in the ocean, and, unfortunately, the use of police radar guns, all measure the Doppler effect of moving objects by bouncing waves off of them. Sound waves in the case of sonar, but light waves in the case of radar. If the object is moving towards the detector, the signal will bounce back at a shorter wavelength, and if it's moving away, the opposite will happen. We use the Doppler effect to detect and track motion toward or away from us. To summarize, imagine a star emitting light with a characteristic blackbody spectrum that has a peak at some wavelength that depends on its temperature. If the star is stationary relative to the observer, so has a velocity of 0, that blackbody peak will appear at precisely the wavelength that corresponds to its temperature. Regardless of how the star is moving, the light that the star emits is always the same, so the true location of the blackbody peak is always at the same wavelength. However, if the star is moving away from the observer, the light that it emits will be stretched out in wavelength. If the star is moving toward the observer, it'll be compressed in wavelength. Now recall that the wavelength of light corresponds to color, just like wavelengths of sound correspond to pitch. Because red light is at the long wavelength end of the visible spectrum, we call the effect of a source moving away from an observer and increasing the wavelength of its emitted light redshift. On the other hand, a source moving towards its observer and compressing its wavelength we call blue shift, since blue light is at the short wavelength end of the visible spectrum. Another important component of the definition is the along the line of sight bit. If the star moves up or down and not toward or away from the observer, its light will be unaffected. Its wavelength will be unaffected. It'll be neither redshifted nor blue shifted. So when we detect the Doppler effect of an object, we're really only measuring one component of its motion, that toward or away from us. If we want to know its side-to-side motion, we have to resort to other tricks. So how does this manifest itself in a detectable way in astronomy? Well, I already hinted at it in my introduction. We usually take spectra to find out what we need to know about an object. You already know that we can take the spectrum of an object and use the peak of its emission to determine its temperature. You also know that we can use the absorption lines in its spectrum as fingerprints to tell us what it's made of. With the Doppler effect, we can use the absolute location of those lines to determine whether the object is moving toward or away from us. A stationary star will have some spectrum with a characteristic set of absorption lines. The thing that's characteristic about them are their spacing and thickness, not necessarily their absolute color. If you take that star and move it away from us, although it's still emitting exactly the same light, every photon it emits will be stretched out a bit in wavelength, and the whole set of characteristic lines will shift towards the red end of the spectrum. So we say it's redshifted. If the source is moving towards us, all of its photons will have their wavelengths shortened a bit, and it will be blue shifted. Not only can we tell from this observation that the source is moving toward or away from us, we can actually tell its speed as well, because the amount by which the lines shift is related to the speed of the object. In mathematical terms, the Doppler effect is expressed as a relationship between two simple ratios. The wavelength shift divided by the so-called rest wavelength, or wavelength of the line if the source weren't moving, is a ratio that tells you how big the shift is as a fraction of the wavelength. It's equal to the speed of the object divided by the speed of light. In other words, the size of the wavelength shift of a line is related to the velocity of that object as a fraction of the speed of light. The bigger the velocity, the bigger the shift. Astronomers use this in a slightly different way, though. They define the term on the right-hand side of the equation, V over C, as the redshift of an object, and they use the letter Z to denote redshift. So redshift is the velocity of the object over the speed of light, or, with a bit of manipulation of the equation to solve for the velocity along the line of sight of an object that's moving away from us is equal to the speed of light times its redshift. We call this velocity the recessional velocity of the galaxy, or star, whatever it is that we're observing, which basically means its velocity away from us along the line of sight. As Maria mentioned last time, it wasn't until Edwin Hubble measured the distance to Andromeda using Cepheid variable stars that people knew how far away galaxies were, that these were distant island universes. But Hubble didn't just do the distance measurement for Andromeda. Together with his colleague Milton Humason, Hubble measured the distances to all of Vesto Slipher's galaxies. What they found was both surprising and profound. Hubble and Humason found that the distance to a galaxy and its redshift were related. Here's some of Hubble's actual data. Each point here represents measurements for one galaxy. The distance to that galaxy is shown along the x-axis and its velocity along the y-axis. This velocity is the aforementioned recessional velocity, or velocity of recession, and it represents a simple Doppler measurement, the speed of light times the measured redshift, as we discussed earlier. It's the speed with which a galaxy appears to be moving away from us, based on the shift in its lines. As you can see from the graph, there's a general upward trend. Nearby galaxies, those with small distances, have small recessional velocities, so they're concentrated in the bottom left of the diagram. And distant galaxies, those with large distances, have high recessional velocities, so are concentrated in the upper right of the diagram. Given the large errors in the measurement techniques of the time, the determination of this relationship was quite remarkable. Here's the data for what the same galaxies look like today with better techniques. This is a very, very tight correlation. Recessional velocity and distance are directly related to one another. As one increases, so does the other. Hubble quantified this relationship with a very simple equation that related the distance to the galaxy, d, with the apparent velocity of recession. He found that this recessional velocity and the distance were directly related through a constant known as Hubble's constant. Hubble's constant, or h0, has a value of 72 kilometers per second per megaparsec. So let's unpack that to understand it. The kilometer per second part is a speed, which is what we want to end up with, and the megaparsec part is a distance. Mega meaning million, and parsec, which you may recall, is a distance measurement equivalent to 3.1 light years. If you measure the distance to a galaxy in megaparsecs and then multiply it by Hubble's constant, the megaparsecs in your distance measurement cancels with the megaparsecs in Hubble's constant, and you're left with a recessional velocity in kilometers per second. So Hubble's law allows you, if you know either the recessional velocity or the distance, to solve for the other through Hubble's constant. Today, we can see even more distant galaxies and measure their distances using techniques like standard candles, and they all hold to Hubble's law. How distant are the galaxies that we see with modern telescopes? Up to a few billions of light years away. So what are their redshifts then? How much are these lines shifted? Here's a timeline showing the age of the universe and the corresponding redshift. First, notice that the scale on the top increases from right to left, and each step along the timeline is not equal. The scale on the bottom, however, is equally spaced and increases towards the right. The top scale is the age of the universe, and the bottom scale is the redshift. To understand what this means, you first need to remember the concept of look-back time. Recall that it takes light from distant objects a finite amount of time, traveling at the speed of light, to reach you as an observer. For this reason, the more distant an object is in the universe, the farther back you're looking in time. This is why the age of the universe increases to the left in the diagram. Things on the left-hand side are the current universe, and on the right-hand side is the birth of the universe. Today, the universe is about 13.7 billion years old, and objects in the very nearby universe have a redshift of 0. Objects at a redshift of 1 emitted their light when the universe was just about 5 billion years old, so more than 8 billion years ago. The faintest objects in the Hubble Ultra Deep Field in the background here have redshifts of about 6, at which point the universe was less than 1 billion years old. And the current record for the most distant object ever imaged is at a redshift of about 8.6, when the universe was just 500 million years old. The James Webb Space Telescope, which is a successor to the Hubble Space Telescope and will be launched within the next 5 years or so, has a goal of being able to see the very first galaxies that formed in the early universe at redshifts of about 15. So I don't know if you've noticed yet, but there's something very strange about this scale, given the previous definition that I gave you for redshift. Remember when I told you that the redshift of an object was equal to its recessional velocity over the speed of light? In other words, what's the velocity of recession as a fraction of the speed of light? So maybe you expected all redshifts to be less than 1. But you can see the scale goes up to 20. So what does it mean if a galaxy has a redshift of 1 or 5 or 15 or 20? Well, to get a value of 1 out of this equation, v and c have to be equal to one another. In other words, the recessional velocity of the galaxy has to equal the speed of light in order to get a redshift of 1. It also implies that objects at a redshift of 2 are moving twice the speed of light, etc., etc. So are galaxies really truly moving away from us at greater than the speed of light? Isn't it a fundamental, unbreakable rule in the universe that objects can't travel this fast? To answer this, let's take a step back and think about what Hubble's law actually means. The fact that every galaxy we see is moving away from us, and the more distant ones are moving faster, implies, first and foremost, that the universe is expanding. This discovery was first met with some excitement, this discovery of Hubble and Humason, that all the galaxies in the universe are redshifted and therefore moving away from us. It was met with excitement because the whole history of astronomy, up to this point, was, as the astronomer Carl Sagan once described it, a series of great demotions. The Earth was not the center of the solar system, and the Sun was not the center of the galaxy, but maybe, people thought, the Milky Way was special. If everything that we see is moving away from us, then the universe must be expanding, and we must be at the center of it all. So is this really what's going on? Everything is expanding away from us at the center? In reality, everything is expanding away from everything else, and the pattern of great demotions continues. The Milky Way is not a special galaxy, just like our Sun and our planet are not intrinsically special. So here's how to think about this. Imagine that you have 5 galaxies, A, B, C, D, and E, that are all close together in the early universe, and then let's expand it. If the space between them expands, then at a later time they might look something like this. Each letter has moved an equal distance away from all the others. And at an even later time it might look like this, then this, then this, then this. All the galaxies are even farther away from one another at each time step. The first thing to notice is that regardless of whether we live in galaxy A, B, C, D, or E, we always see all of the other galaxies moving away from us as the universe expands. At each time step, all the galaxies get farther away. Consider, for example, galaxy C. As the universe expanded here, all of the other letters moved away from it. The same is true for galaxies A, B, D, and E. From their perspective, all the other galaxies are moving away as the universe expands. So this is the first observable phenomenon. In an expanding universe, every galaxy sees all other galaxies moving away from it. None of them are the center of expansion, or if you prefer to be more optimistic, all of them are the center of expansion. In fact, as far as we know, there's neither a center nor an edge to the universe. And if we have time, we'll talk about this in more detail in later classes. A second observable is that the speed with which each galaxy appears to travel varies. For example, galaxy D moved from here, from galaxy C's perspective, to here as the universe expanded. So it moved this much in total. In the same amount of time, galaxy E moved from here to here from galaxy C's perspective. It moved this much. Just the effect of proximity to the galaxy doing the observing means that more distant galaxies appear to be moving farther in the same amount of time. Farther in the same amount of time means they appear to be moving faster. Is galaxy E actually physically moving away from galaxy C, though? Is it really moving faster than galaxy D? In reality, these galaxies themselves aren't moving at all. The space between them is expanding. The expansion of the space between them makes them appear to be moving away, but in reality, this is an optical illusion created by the expansion of space between them. So this solves our problem of galaxies appearing to move faster than the speed of light. In short, they're not. The effect of the expansion of space appears more extreme the farther out you look. The galaxies aren't physically zooming through space away from us, they're expanding with space. The universe expands by about 7% every billion years, so you might picture the expansion of the universe as something like a copy machine, where you blow up your page to 107% of its current size every billion years. Bigger and bigger and bigger. So is this a good way to imagine it, do you think? Do you see anything wrong with this picture? Well, as I've been going along here, you might have noticed that I was careful to say that space expands. Galaxies and the stars and planets within them don't expand. So this is a more accurate picture. These clusters of galaxies remain the same size, bound together, and the spacing of the galaxies within the cluster also remains the same. But the space between clusters expands. Expansion is a property of empty space, and we'll talk about it more in a later lecture. This actually tells us now why the Andromeda Galaxy and a few other nearby galaxies can be blue-shifted relative to us in an expanding universe, which I've pretty much ignored in this lecture up until now. As Maria mentioned last time, Andromeda is moving towards us because it's gravitationally attracted to us. It's not moving away with the expansion of the universe because it lies within our own local group of galaxies where space is not expanding because it's not empty. The picture of expanding space, though, presents a problem with some of our earlier assumptions. Namely, that the redshifts that we see in distant galaxy spectra are because of the Doppler effect. Although we keep the mathematics and terminology I've already introduced, recall that it's not truly a recessional velocity because it's not the galaxies that are moving away from us, but rather space that is expanding between galaxies. If these galaxies aren't physically moving away from us, but are locked to an expanding space, then what causes their light to be redshifted? Well, light, unlike galaxies, doesn't have mass. And as it travels through space, it expands with it. If you picture a photon of light with some wavelength emitted in the early universe, then as long as it's traveling through space, it will expand with it. It'll expand more and more as it travels farther away from its source. The longer it travels without hitting something, the more the universe will have expanded since it was emitted. The expansion of the light takes the form of a lengthening of wavelength. The wavelength of the light gets longer and longer, and therefore redder and redder as it travels through the expanding universe. When we intercept a photon emitted from a relatively nearby galaxy, the time it took the photon will be relatively short, and the universe will have only expanded a little in that interval, stretching the wavelength of the photon out just a bit. For a very distant galaxy, the universe will have expanded a lot in the time it was traveling, and its wavelength will have lengthened a lot. It's important, therefore, that you realize that although we measure so-called recessional velocities, what we're measuring is not really a velocity, but the amount of stretching of space that has occurred in the wavelength of light emitted by a source as it traveled to us through the expanding universe. We call this phenomenon cosmological redshift to distinguish it from Doppler redshift, this phenomenon by which the wavelength of light is stretched out by the expansion of space as light travels through an expanding universe. I'll leave you here with the big takeaways from this lecture to contemplate. And next class, we'll talk about the reason for this expansion of the universe, namely the Big Bang.